The global chip war is here, and China's supremacy might already be unstoppable. Right now, every phone you unlock, every AI model you ask a question, every missile defense system protecting a nation, all of it runs on semiconductors. And the country that controls how those chips get made controls the future, today. Over 90% of the world's most advanced chips are manufactured by a single company on a single island, and China has just committed over $150 billion to make sure that dependency ends. That's more than the entire GDP of Hungary. You heard that right. One country's chip budget now exceeds the total economic output of a European nation. And to understand why that bet might actually pay off, you need to see how the system China is trying to replace was built in the first place. The machine behind the machine. If you want to understand why the chip war matters, you first need to understand the system everyone is fighting over. And once you see how it works, you'll realize why most people, even in tech, don't fully grasp how fragile it really is. The modern semiconductor supply chain isn't owned by one company or one country. It's an interlocking web that stretches across continents. And every single link in that chain is a potential choke point. Start at the top. When a company wants to design a cutting-edge chip, it doesn't just sketch something on a whiteboard. It needs electronic design automation software, EDA tools, and there are only two companies on the planet that make the advanced versions, Synopsys and Cadence, both American. Without their software, you can't even begin designing a high-performance chip. You're stuck at the drafting table. But designing is only the beginning. Once that chip is designed, someone has to actually build it. And when it comes to manufacturing the most advanced semiconductors, we're talking anything at 7 nanometers or below, there is essentially one company on Earth that can do it at scale. That's TSMC, the Taiwan Semiconductor Manufacturing Company. Over 90% of the world's most advanced chips flow through their fabrication plants on an island roughly the size of Maryland. Let that satisfy for a second. The beating heart of the entire global technology economy sits in a space smaller than most American states. But even TSMC can't do what it does without the right equipment. And this is where the chain gets even thinner. To print transistors at these impossibly small scales, you need extreme ultraviolet lithography machines, EUV machines. Each one costs around $350 million, weighs over 180 tons, and contains more than 100,000 individual parts. And there is exactly one company in the world that makes them, ASML, based in the Netherlands. One company, one machine, no alternatives. Number one. Now layer in NVIDIA, whose GPU architectures power nearly every serious AI workload on the planet. Layer in the specialty chemicals, the ultra-pure silicon wafers sourced from Japan and Germany, the precision optics, the testing equipment. What you end up with isn't a supply chain, it's a dependency architecture. Every piece relies on every other piece, and almost all of the critical nodes sit in the hands of American companies or close American allies. And that's exactly what made it so tempting to turn this system into a weapon. The stranglehold. In October 2022, the United States made one of the most aggressive technological moves in modern history. Washington didn't send troops. It didn't impose traditional sanctions. Instead, it did something far more surgical. It tried to freeze China's entire semiconductor industry in place. The export controls that rolled out were unlike anything the chip world had ever seen. The US didn't just block China from buying the most advanced finished chips, it went deeper. It restricted access to the equipment needed to make those chips. It cut off the software used to design them. And then, it went further still. It barred American citizens and permanent residents from working in Chinese semiconductor facilities. Think about that for a moment. The United States essentially told its own people that helping China build chips was now a matter of national security. But Washington knew it couldn't do this alone. The most critical choke point, EUV lithography, wasn't even American. It was Dutch. So the US leaned on the Netherlands to block ASML from shipping its most advanced machines to China. Then it pressured Japan into restricting exports from Tokyo Electron and Nikon, two companies whose equipment is essential for chip fabrication. Within months, A coalition had formed not a military alliance, but a technology blockade designed to keep China locked out of the frontier. The strategy had a name in policy circles: small yard, high fence. The idea was simple. You don't need to restrict everything. You just need to identify the technologies that matter most, the highest-end chips, the most advanced tools, and build an impossibly high wall around them. Let China have the older stuff. Let them make legacy chips for appliances and cars. But the cutting edge, the chips that power AI training, advanced weapon systems, and next-generation computing, those would stay out of reach. And for a brief window, it looked like it was working. Chinese companies scrambled. Huawei's chip division took a serious hit. Orders for advanced equipment were canceled or rerouted. Headlines declared that America had found the kill switch for China's tech ambitions. But here's what almost nobody was talking about. China had been preparing for this moment for years, and the response that was already underway would dwarf anything Washington had anticipated. The war chest. When the export controls hit, most Western analysts expected panic. They expected delays, setbacks, maybe even a quiet acceptance that China would have to settle for second-tier technology. What they got instead was the largest state-directed investment in a single technology sector in human history. China didn't flinch. It doubled down. The vehicle for this counterattack is something called the National Integrated Circuit Industry Investment Fund, known simply as the Big Fund. Its first phase launched back in 2014 with about $20 billion. That was the warm-up. Phase 2 came in 2019 with roughly $29 billion more. And then in 2024, Beijing unveiled Phase 3, a staggering $47 billion in fresh capital, making it the largest single tranche of semiconductor investment ever deployed by any government. And that's just the Big Fund alone. When you add in provincial government subsidies, tax incentives, state-backed loans, and direct equity injections from local governments competing to build their own chip hubs, the total figure climbs past $150 billion. Some estimates push it closer to $200 billion. But what makes this dangerous isn't just the money. It's where the money is going. China isn't placing a single bet on one company or one technology. It's targeting every single link in the chain simultaneously. SMIC, China's most advanced foundry, is receiving billions to expand capacity and push towards smaller nodes. Huawei's chip design arm, HiSilicon, is quietly rebuilding its capabilities. SMI, Shanghai Microelectronics Equipment, is racing to develop domestic lithography machines. And then there are hundreds of smaller companies' firms you've probably never heard of, working on photoresists, etching equipment, deposition tools, silicon wafers, and EDA software alternatives. You need to understand what this means strategically. China looked at the dependency architecture you learned about earlier, the one where every critical piece runs through American hands or American allies, and decided to build a parallel version of the entire thing. Not just one piece, all of it, from raw materials to finished chips. Now, skeptics will tell you this has been tried before. They'll remind you that the Soviet Union tried to build an independent semiconductor industry and failed. They'll point out that money alone doesn't solve physics problems, that chip making is the most complex manufacturing process humans have ever devised, and that decades of institutional knowledge can't just be purchased. And they're not entirely wrong, but what they're missing is what China brings to this fight that no previous challenger ever had: the other way in. Here's what most people get wrong about China's semiconductor strategy. They assume the goal is to copy what already exists to somehow replicate ASML's EUV machine, clone TSMC's process nodes, and rebuild the Western supply chain piece by piece. But that's not what's happening. China isn't just trying to walk the same path, it's cutting new ones. The first route is something called multi-patterning lithography. To understand why it matters, you need to know what EUV actually does. An EUV machine uses extremely short wavelengths of light to etch incredibly fine patterns onto silicon wafers, patterns so small that you're working at the scale of individual atoms. Without EUV, the conventional wisdom says you simply cannot produce chips at 7 nanometers or below. But in 2023, Huawei stunned the world when it released the Mate 60 Pro smartphone, and inside, it was a 7nm class chip manufactured by SMIC, without a single EUV machine. How? Multi-patterning. Instead of using one sophisticated exposure, you use older DUV machines and expose the wafer multiple times, layering patterns on top of each other to achieve finer resolution. It's slower. It's more expensive per chip. The yields are lower. But here's the part that changes the equation. When your government is subsidizing the cost and your domestic market is guaranteeing demand, those trade-offs stop being deal breakers. They become manageable engineering problems, and China has shown it's willing to absorb those costs for as long as it takes. But multi-patterning isn't the only card on the table. The second pathway is advanced packaging, and this one might matter even more than node size. See, the industry has been obsessed with shrinking transistors for decades. Smaller nodes, more performance. But there's another way to boost what a chip can do, and that's by changing how you put chips together. Chiplet architectures and 2.5D and 3D packaging allow you to stack or connect multiple smaller chips into a single package that performs like one massive processor. TSMC's CoWoS packaging is what makes NVIDIA's most powerful AI chips possible, and China is investing heavily in domestic alternatives to that exact technology. If you can master advanced packaging, you don't need to match TSMC node for node. You can build competitive systems from slightly less advanced components and still deliver the performance that matters. Then there's the third pathway, and this is the one that should keep Western policymakers up at night. China is pouring resources into next-generation lithography research approaches that don't just work around EUV, but aim to leap past it entirely. Particle beam lithography, X-ray lithography, techniques that are still largely experimental in the West, but are receiving serious, sustained funding from Chinese national laboratories and synchrotron research facilities. China's Hefei-based synchrotron light source and the Shanghai Synchrotron Radiation Facility aren't just academic projects. They're infrastructure bets on a future where the lithography bottleneck doesn't just get solved, it gets made obsolete. And here's the part that nobody is saying out loud. If even one of these alternative pathways reaches production scale, the entire logic of the export controls collapses. You can't block someone from buying a machine they no longer need. But the engineering isn't even the most underestimated part of China's position. The real advantage runs deeper than any single technology. The factory floor of the future. Technology gets all the headlines, but wars aren't won by blueprints. They're won by the systems that turn blueprints into reality. And this is where China holds advantages that most Western analysts consistently underestimate. Start with talent. China graduates over 5 million STEM students every single year. That number alone is staggering, but what matters more is how Beijing is directing that pipeline. In 2021, China designated integrated circuit science as a first-class academic discipline, a bureaucratic move that sounds boring until you realize what it unlocks. It means dedicated funding, dedicated faculty lines, and dedicated recruitment pipelines flowing straight from universities into semiconductor companies. On top of that, thousands of Chinese engineers who spent years working at Intel, TSMC, Samsung, and ASML have been returning home, bringing with them exactly the kind of institutional knowledge that money alone can't buy. The very expertise the export controls tried to contain is already inside the walls. Then there's the speed factor. You've watched China build hospitals in 10 days and lay down high-speed rail networks that took other countries decades to plan. That same industrial velocity applies to chip-making infrastructure. When SMIC needs a new fabrication plant, it doesn't spend 7 years in regulatory review. Construction timelines in China routinely come in at half or even a third of what comparable projects take in the United States or Europe. Intel's new Ohio fab broke ground in 2022 and isn't expected to produce chips until 2028 at the earliest. Chinese fabs operating on similar timelines are already producing wafers. In a technology race, speed isn't just an advantage, it's a compounding one. Every month you build faster is a month your engineers spend learning, iterating, and improving yields while your competitor is still pouring concrete. But perhaps the most overlooked advantage is the one hiding in plain sight: China's domestic market. China buys more semiconductors than any other country on Earth, importing over $300 billion worth annually. That enormous demand creates something invaluable for any emerging industry: a guaranteed customer base. Chinese chip makers don't need to compete on the global market from day one. They just need to be good enough for domestic consumption. And good enough is a powerful launchpad. It gives companies room to ship imperfect products, collect real-world performance data, improve their processes, and scale, all while generating revenue. Every major semiconductor power in history followed this exact trajectory. The United States did it with military contracts. South Korea did it with consumer electronics. Now China is doing it with the largest electronics market the world has ever seen. These aren't advantages that show up in a quarterly earnings report. They're structural forces that compound over years and decades. And when you stack them on top of the engineering pathways China is already pursuing, a very different picture starts to emerge. The question is no longer whether China can build chips. It's whether anyone has the right framework to understand the race they're actually in. The long game. Here's where you need to step back and rethink everything you've been told about this race. Because the way the chip war gets covered, who has the best chip today, which company hit the smallest node first, whose stock price jumped after an earnings call, all of that misses the point entirely.
The chip war isn't about who's leading right now. It's about who's building the most complete system for what comes next.
And when you look at it through that lens, the picture shifts dramatically. Think about what system completeness actually means in semiconductors. It's not enough to design a great chip. You need the software tools to design it. You need the raw materials, ultra-pure silicon, specialty gases, photoresists. You need the equipment to deposit, etch, pattern, and inspect at nanometer precision. You need the foundries to fabricate at scale. You need advanced packaging to assemble the final product. You need testing infrastructure to verify every single die. And you need the trained workforce to operate, maintain, and improve all of it continuously. Miss any one of those links and your entire chain breaks. Right now, the Western system is the best in the world. That's not up for debate. But here's what you need to understand about how that system is built. It's distributed. ASML sits in the Netherlands. TSMC sits in Taiwan. Design software comes from California. Precision optics come from Germany. Specialty chemicals come from Japan. This system works beautifully when everyone is aligned, but it requires constant coordination across multiple governments, multiple corporate interests, and multiple political cycles. One election, one trade dispute, one shift in diplomatic priorities, and a critical node in that chain could wobble. China is building something fundamentally different. Its system is consolidated, centrally directed, optimized not for peak performance today, but for resilience and independence over the long term. Yes, it's less efficient right now. Yes, the chips coming out of Chinese fabs aren't matching what TSMC produces at 3 nanometers. But efficiency isn't the metric that matters in a strategic race. Endurance is. China's system is designed to absorb losses, tolerate lower yields, and keep iterating without needing permission from anyone. No allied coalition to maintain. No shareholder pressure demanding quarterly returns. No democratic elections that could reverse industrial policy overnight. And that brings you to the question that almost nobody in Washington or Brussels or Taipei wants to sit with honestly. In a race that plays out over 10, 15, 20 years, which architecture has the structural advantage? The distributed system that's more advanced but more fragile? Or the consolidated system that's less sophisticated but more resilient? You don't have to answer that question right now. But you do need to understand that China has already answered it for itself. And it's building accordingly not for this quarter, not for next year, but for the next generation. And what that generation inherits might look nothing like what any of us expect. The inevitable equation. So now you've seen the full picture. You've seen the system the West built brilliant, intricate, and dependent on every single piece staying exactly in place. You've seen the stranglehold Washington tried to impose, and the brief window where it looked like it might work. You've seen China's response, not a scramble, but a calculated $150 billion march toward total self-sufficiency. You've walked through the alternative engineering pathways that are already producing results nobody predicted this soon. And you've seen the structural advantages, the talent, the speed, the market gravity that make China's position fundamentally different from any challenger that came before it. But here's what it all comes down to. The export controls were built on a single assumption that China could not build what it could not buy. That the gaps were too wide, the physics too hard, the institutional knowledge too deep to replicate. And for a while, that assumption held. But every month that passes, it holds a little less. SMIC is fabricating chips that weren't supposed to exist without EUV. Advanced packaging breakthroughs are closing performance gaps that were supposed to take a decade to close. Domestic lithography programs are hitting milestones ahead of schedule. And an entire generation of Chinese engineers, 5 million new STEM graduates entering the workforce every single year, is being shaped by one mission wired into every incentive structure around them. Solve this problem. You're not watching a country try to catch up anymore. You're watching a country try to make the very concept of catching up irrelevant by building a system so complete, so internally resilient, that the choke points the West spent decades creating simply stop mattering, not because they were broken, but because they were routed around entirely. The chip war was never going to be decided by who had the best machine in 2024. It was always going to be decided by who built the most complete and unbreakable system by 2035. And right now, only one country on Earth is building with that timeline in mind.